All right, so yeah, again, it's a great pleasure. And I think we had enough plugins already for our hosts for this meeting. So you've already seen in this session a number of dynamic phenomena, and this is what I will jump right in, following what Pablo already showed and Dmitry, especially on the ultrafast regime of things. I just want to be careful that I'm kicking the laptops around here. So I will extend actually some of the concepts which were already highlighted, especially in the coherent ultrafast regime. You have seen phononic and polaritonic properties and propagation. These are already coherent, but not quantum coherent phenomena. And then yesterday, from work from Rupert's group, you have seen dynamic phenomena also extending into the atomic scale. And what I will show you is also what's been enabled by a unique tool from our group, where we really nano-focus or nano-localize a few femtosecond light pulses then into the apex of the tip, and this allows us then to do second and third and also higher order nonlinear optical interactions, which allows us to really turn an ultrafast movie of the coherent evolution of coupled quantum excitations, and I'll show you sort of a little bit the development of this method, and then also the recent application to probing exciton coherence in a excitonic transition metal like hydrogenide, and then also you've seen a lot of the exciting physics which results from multilayers and heterostructures, and I'll show you actually how we resolve and distinguish dynamic processes in hetero-bilayers and be able to actually separate whether charge or energy transfer dictates actually the physical processes. So the work is that actually of Wenjin Luo, who is postdoc in the group, just returned to China and succeeded by Ben Wetten, a brilliant graduate student, in collaboration, a lot of work with former postdoc, now professor at Tongji University, and also Vasily Krastov in Russia. And I have to say that a lot of the interpretation on the quantum dynamics is actually of the results from theory work from Alexei Belyanin from Texas A&M. And of course, our friendly host is providing instrumentation, although I have to say not for this experiment. So that's all home-built instrumentation. So it's obvious to you now that the scanning probe optical nano-imaging is the tool of the trade for a lot of 2D material physics and how you want to probe coupled electronic spin and lattice excitations on the nanoscale with added benefits where the tip also provides other means of nano-localized control interactions, for example, inducing strain, but also and this is what I'll show you at the end, where the tip and the sample actually form a picocavity which modifies the light-matter interaction itself. And this can also go into the strong coupling regime. But what we take advantage of here is in recoupling, where we benefit from the Purcell enhancement of the tip, which selectively modifies the radiative relaxation pathway, which allows us to distinguish actually these competing interactions between radiative and non-radiative processes, where the non-radiative processes are the interlayer energy and charge transfer. So the group, we work a lot actually, in fact more than on 2D materials, in molecular systems where we probe vibrational excitations and also quantum coherent dynamics, and this is really what I'll show you, how we actually turn ultrafast movies and information we extract. So that this complements a lot of development in the field of ultrafast electron and X-ray microscopy. And I should actually say, in many ways, these techniques have progressed in fact much faster than many methods in nano-optical probe spectroscopy in the combination with ultrafast spectroscopy. And this is because lots of X-ray sources were already always on the femtosecond scale. And then also the generation of ultrafast electron pulses has progressed very rapidly, allowing with many leading groups actually in Germany on ultrafast electron microscopy. So in some way, and this is sort of a call out at the community, we are actually almost still catching up of combining ultrafast spectroscopy with scanning probe microscopy. Yeah? And so the sort of the roadmap and many applications which we pursue is one big goal is far from equilibrium excitation and doing this in a quantum state resolved way in scanning probe microscopy. And we work on perovskites, for example. There was a nice example also shown yesterday. And the focus of the talk really now is on the coherent interaction, and especially really this coherent dynamics on the nanometer and femtosecond scale. And that really requires a special tool. This is not able where you cannot trivially extend what you've learned in coherent spectroscopy and wave mixing in multidimensional coherent interactions. This is not trivially applicable actually in the scanning probe microscopy because you're losing features due to the k-vector and momentum matching. So we have to actually play a couple of tricks, and this is what I'll show you briefly, and I'm happy to talk more with you individually later for those who want to implement this. So again, we're using a nano-localized source for femtosecond excitation, and I'll show you the method how we actually do in coherent four-wave mixing, being able to measure coherent dynamics in actually an electronic resonance system, so we're using graphene. Then I'll show you what changes and what's sort of the key distinction of electronic coherence in graphene versus an excitonic excitation in a transition metal dichalcogenide. And then we'll apply this also then with a device engineering trick, how we can actually resolve combining two-photon photoluminescence and four-wave mixing, and the difference in that this provides an incoherent and this is a coherent signal, how we can actually then separate energy and charge transfer in hetero-bilayer systems. So, okay, I don't need to show more on this, that this is the ideal tool of the trade here for lots of 2D materials. And so what I'm tying in here is really that there are two significant properties which actually haven't been spoken about much, and one is actually the nonlinear response of 2D layered materials is very unique. You can drive resonant interaction, which gives you actually not only a very high optical nonlinearity, but then also a very efficient generation, which is of course normalized by the volume, a small contribution, but then it outperforms the otherwise linear absorption of the nonlinear generated signal, and this is actually where you benefit a lot on these strong nonlinearities if you actually do this in a two-dimensional system. And the other aspect related to coherent nonlinear optics is, of course, the coherence itself. And this has been studied actually in a number of examples, and a lot of open questions emerged that the notion initially expected that you have very long coherence times has actually not been really verified. This is actually still modest numbers, and these are actually at very low temperature, where you actually have a lot of decoherence pathways which are frozen out, and yet it's not clear then especially whether these numbers are limited by the inhomogeneity, the spatial inhomogeneities in the system, or whether they are fundamental, and this is why we want to do spatially resolved imaging. So the way we really generate now our femtosecond nano-localized light source is that we actually, in contrast to the applications you've seen before, is that we are not illuminating the sample directly, or we're not even illuminating the tip apex region directly, that we actually, in the tens of micron distance, we actually generate a propagating surface plasma polariton with a grading coupler, and then this surface plasma polariton actually undergoes some magic as it propagates to the apex and really forms the femtosecond nano-localized source. And the mechanism is actually that we have a decrease in the group velocity because of an effective increase of the index of refraction of light, and this then gives rise to the fact that this optical field, as it propagates on this conical waveguide, does not actually radiate as the radius becomes smaller and comparable to the wavelengths. So this is normally how you would then get radiative losses when the structure is inhomogeneous on the scale of the wavelengths. And so what happens here, and we have actually measured indeed, that this decrease of the group velocity gives rise to a decrease in the wavelengths, which is more efficient, and it shortens faster than the radius decreases. And this actually then gives rise to the fact that at the very apex, when this propagating field is turned back into a localized radiating dipole that the group velocity is actually 20% of the speed of light. So it's actually nice to talk about this in the presence of the mountains, you know. So just like the tip, this is a very unique topology, right? So that's that we're only in the propagation direction. Yeah, there is a broken translational invariance in that broken in this direction only at the very apex. And this is why I like to stand on the top of a mountain, because that's where your perception of the world is different. And this is the same as you can picture for this propagating surface wave, which perceives its translation invariant space and doesn't know what happens to it, that it slows down and gets compressed into this apex field. So we are using now this strongly localized field, which is again a few femtosecond pulse. We can actually compensate with pulse shaping techniques the dispersion. So we actually use the second harmonic generation of the apex, which with pulse shapers generates pulse replica, which we use then to excite the coherent excitation at the apex. And then we program pulse transients in the apex. That could either be a very short controlled pulse with a controlled phase, or it could be pulse sequences. And so then the kind of signal we look at, so this would be the spectrum of about a 10 femtosecond pulse at the apex. We have a programmable filter which cuts actually the long wavelengths region. And then we use this four-wave mixing process of the remaining spectral distribution of the field to reconstruct actually the portion of the light which we have removed, where then this process gives rise to then again reconstructing the high energy photons. So we can do this directly in the time domain, or we can actually do it in the frequency domain spectroscopy, where we again reprogram the pulse shaper to generate then longer but spectrally narrow pulses, and then we can use the four-wave mixing or other signals then in doing spectral domain microscopy. So here's what I just showed earlier, that we can compensate group velocity and third order dispersion and really have this controlled field at the apex. Now, what do we want to use it for? And this is a very general way of the desire to do coherent four-wave spectroscopy, is really that you want to look at heterogeneity or coupling of coherent emitter which experience locally different environments, and this gives rise then to different coherence times and of course different resonance frequencies of an emitter. And this is essentially what you deal with when you look at a material and have any form of heterogeneity. So the way where we demonstrated this was actually in a dense electron system. These are localized surface plasmons at a gold metal edge, and then we can actually, by varying the delay between the two pulses in this correlated measure in this four-wave mixing the decoherence of these localized surface plasmons within the bandwidth of the spectrum of the excitation pulse. And then they decay extremely fast, and this is what you expect for a true metal, but they decay differently. You can see this when you normalize these signals. And then there is coupling and energy transfer between these coherent excitations, and you can actually also model this. So ironically, this work which we demonstrated actually pushing now 10 years ago, this is actually still the fastest movie. It's a short one, but it's still one of the fastest movies ever made. So now we want to apply this to 2D materials. So graphene is the example of choice. In graphene, you actually expect also very fast coherence times, and this is because of the weak screening. So now here we're looking at a monolayer and multilayer of graphene sheets, and the signal is that of the four-wave mixing signal. And then we can look at spatial heterogeneity again and the decoherence time, and this is about as fast as what's the limit of the technique with which we can resolve it. So we have actually coherence times of 6 femtoseconds. And ironically, when we did this work, this was sort of just around where people were wrapping their mind around why it could actually be so extremely short. And this is because of this weak carrier-carrier screening you have in this 2D layered material. And so you get very fast, actually, Auger recombination and also impact ionization. So you're very much in this quantum coherent regime just before you get to this Landau-Zener transition. And this is the mechanism, a pure electronic process of essentially unscreened carriers, and this is that fast. It's not a result of the heterogeneity. In fact, we see a weak correlation of the signal with spatial heterogeneity, and this is because if your process is intrinsically that fast, then any defects or other differences to the coupling to the underlying substrate. And to preempt this question, yes, no, this was not affected if you actually put this in boron nitride or not. This will have very little effect on this, on these extremely fast timescales. So this is intrinsic and therefore at that speed very much unaffected by heterogeneities. So, but this is very different now if you look at transition metal dichalcogenides and look at the exciton resonance. So the experiment's very similar. Now we have the resonant interaction with the A exciton. And so then we also then not only see the four-wave mixing, but we also have the two-photon photoluminescence or the second harmonic. And so we do these experiments in this system. Now we are seeing much longer coherence times, but only locally. Yeah, so now we get up to 60 femtoseconds at certain sample locations, but elsewhere it's extremely short as well, and even below the resolution, spatially varying on 50 to 100 nanometer length scales. And this is because the mechanism here is very different for the decoherence. The decoherence for excitons is due to exciton phonon scattering. And if you actually take theory from Selig and others, and they actually showed that when you do these measurements at room temperature, you actually expect generally extremely short coherence times, but our time scale actually even exceeds what was predicted in the model. So the model actually is assuming a very strong electron-phonon interaction. And so it appears that there is other mechanisms which can actually protect coherence for longer time scale at locations. We don't exactly know, of course, what the structural differences are, why they actually exhibit longer coherence, but we have now this higher sensitivity to spatial inhomogeneities because as you have this coherent evolution, it will live for longer. So I don't have time to talk much about really unique phenomena of the electronic coherence on the nanoscale. We see, for example, a inverse correlation of intensity with timescale. So actually we get higher signal intensities for shorter coherence. Yeah, this is a very unique effect which you can imagine in nano-localized excitation, whether you have weak disorder and have disorder-induced decoherence, or whether you have actually forms of strong disorder in exciton localization. So I will not talk about this. Maybe in the last minute, I'll show you now how we actually use this process to look at interlayer excitations. And in all these systems, which many of you love, a big question is whether it is dominated by charge or energy transfer, whether it is actually a tunneling effect or whether it's sort of a dipole-dipole interaction which controls the interlayer coupling. And this is what we can resolve with this approach. Now, looking at both the multiphoton excitation versus the coherent interaction, and we're doing this here at an example of graphene on tungsten diselenide. So now we have signals from both samples. And maybe to get to the bottom line, the way we now can separate the process is by the insertion of a boron nitride interlayer, because the charge transfer is suppressed on short length scale if it were tunneling. But if it were a Coulomb interaction with a longer interaction, then the energy transfer would be less affected by the boron nitride. So we do this, so inserting this interlayer, besides walking you through the images of all the different heterogeneities, what we can show really is that the interlayer relaxation is actually controlled by the long-range Coulomb interaction. And now the feature of a local probe technique is that now we can actually pick sample regions. We image, probe the four-wave mixing signal, look for where we have long coherences, and then we do local probe spectroscopy where we actually do distant dependent scans where we modify actually the coherence and the emission through the Purcell effect of the tip. And from modeling these data, we can actually then extract a number for this energy transfer rate. And this energy transfer rate is on the order of a few hundred picoseconds. And this actually is in good agreement what people have seen in using now very complex large area samples which they need for RPIS measurements, and in time-resolved RPIS here from the Berlin group from Ralf Ernstdorfer, they have actually attributed this interlayer energy transfer to an Auger process of the same time scale. So you can do a lot of things with local probe coherence spectroscopy, literally in a much smaller footprint and on any form of sample by locally selecting your homogeneous samples rather than going through this arduous effort of probing, of engineering really large area samples, which is necessary for for electron spectroscopists. So with that, let me summarize. I showed you that technique to really probe ultrafast electronic coherence, and then in a number of examples, whether you have fast electronic coherence in graphene, electron phonon-induced decoherence in excitons, and different wide playground how you can actually look at interlayer processes and resolving then the different coupling mechanisms. And the key take-home message is in coherence, really the fastest dynamics is actually least sensitive, of course, to structural heterogeneities, and of course, the slower the coherence time, then you have a lot more opportunities for this coherence to be lost through static or dynamic disorder. And I think with that, I'd like to summarize and thank you for your attention, and maybe have a shameless plug-in that we have actually a conference on ultrafast optical processes and semiconductors in Newfoundland in St. John's, so we still are open for abstract submission if anybody's interested. Then we'll hope to see some of you there, and otherwise I thank you for your attention.
So we have time for a couple quick questions.
Yeah, so that is possible, and so we can do this with phase cycling in this pulse sequence. Now, on the other hand, there is also a question on whether it is actually necessary. So the purpose of multidimensional coherent spectroscopy is, of course, to unravel what's your homogeneous sample response. And in these systems, the heterogeneity is the spatial inhomogeneity in the material. So if I do local probe spectroscopy and get then to 60 plus femtoseconds, say, in this tungsten diselenide, I would argue that this is actually the homogeneous sample response, and probably even longer than what you get in a coherent 2D spectroscopy experiment where you would attribute this. But of course, nevertheless, it's still important intellectual gymnastics to then say, well, yeah, can we actually do multidimensional coherent spectroscopy on the nanoscale? So, but it's hard. Okay, the signal is just spread on yet another axis, and that makes it hard. Yeah.
Other questions?
Difference between the electronic coherence and the exciton coherence is based on some spectral changes when you are exciting those coherences in your method. And also I was wondering, like, what is it that is really changing the coherence there for both of the cases? Is there any strains or any material differences which are causing this?
Yeah, okay. So that's a wide spectrum of questions in a way, right? What are the different decoherence mechanisms and the function of energy of the excitation, and which population of electrons, or which subset within the density of states of the carriers are actually involved. So in the graphene, it's the continuum of states in the Dirac cone. In the other case, it's selectively the exciton resonance, right? And that's the difference. And so in the electron continuum, this is where these carriers are scattering above with each other in this excitation above the Fermi level, right? And the exciton is just that it is the excitation of the exciton, which then couples to the electron phonon interaction to the phonon bath, right? And it's that fluctuation which gives rise to the decoherence. But yeah, that's very key, of course, to be very specific of what electron population or what subset of carriers you're actually talking about, right? Because that can have, it's not all carriers, even in the same system, don't all have the same decoherence. This is very important. I appreciate that question, actually. Yeah.
I think there was one question in the back. Wasn't there one question in the back? Oh, okay, thank you. If I asked you one quick question, I don't think you mentioned this probably because you ran out of time. One of the things that we often ignore about these near-field measurements is you kind of get strong coupling for free.
I wish. So you do get strong coupling if you have a plasmonic tip, and typically in the presence of a metallic substrate. So then, and we could show this on quantum dots, then you do get strong coupling because of the small mode volume. In these experiments, and this is the detail of that formalism there, where we are not in the strong coupling regime, but the tip modifies the electromagnetic density of states to the extent that we see the Purcell effect. And so that gives rise to the acceleration of the radiative emission and increase of quantum yield. So that you get more for free. The strong coupling is still an exercise. Yeah. So yeah.